Okay. Yeah, so this project came out of a semester that was spent at the Hausdorff Institute of Mathematics last summer. And it was a co-author with Emily Riehl from Johns Hopkins University. And this was really actually essential to this project. So I am I would say I'm a lean formalization expert. I took a category theory class once, you know. Emily is a infinity category theorist with a bit of lean experience. And so while we were there together in Bonn, I suggested that we try to sort of define the fundamentals of infinity category theory in lean, because I know that this is an area that's lacking, and I thought it would be an area that would be interesting to us both. So it turns out that infinity categories are complicated to define. It's actually not even really clear what the definition should be, and like if you choose a definition, it sort of puts constraints on how you want to formalize things later. But there's another way of doing the definition where you actually don't really do a definition, but you give sort of constraints around what the definition ought to be. I think of this as sort of analogous to how you need to define what's a universal computation, and you have to make a decision about whether you're talking about partial recursive functions or Turing machines or something like that. And they're all kind of the same, but they all add their own mess. And so maybe you just define some kind of abstract thing that's sort of equivalent. And so the Infinity Cosmos project came out of this. Infinity Cosmos is basically a way of using a convenient abstraction boundary to formalize some of the core category theory of infinity categories for use in MATLAB. And so MATLAB knows the definition of an infinity groupoid. That's a weak infinite dimensional category with all of the morphisms above the first level invertible modeled as Kahn complexes. And infinity categories can be defined in MATLAB as well using quasi-categories. So this is, actually, no, I'm not going to describe what it is. You have non-invertible morphisms. But very few theorems have been proved about these notions. There is not actually the definition of like a proof of associativity of composition, or that there exists an associator. And the definition of Kahn complexes was discovered to be wrong just earlier this year. So, you know, this is the situation where no one's really even used these enough to notice sort of kind of obvious issues once you actually try to use it properly. So the project is underway, and you can see there's this is a picture from the blueprint for Infinity Cosmos, and you can see that there's a lot which hasn't been done. But okay, so you can have, there's a way of reducing infinity category theory to two-category theory in a way. So there's a two-category whose objects are infinity categories, the morphisms are infinity functors, and the two cells are infinity natural transformations. And so that means that we can sort of reuse a lot of the existing stuff on two categories, which exists in MATLAB, in order to prove things about infinity categories. A key part of this construction involves this thing called the nerve of a category, as well as its left adjoint, which is the homotopy functor. And so that's kind of going to be what this talk is about. So MATLAB already had the definition of nerve. And so this talk is really about how we constructed the homotopy functor. So let me define what that is. And I have to start with the simplex category. So the simplex category is a category which its elements are just the natural numbers. And the morphisms are monotone functions on the sets. So this bracket n means the numbers from 0 to n inclusive. So it's like fin n plus 1. And so if we're looking at monotone functions from the numbers up to n to the numbers up to m. So for example, there's exactly one morphism from 1 to 0. That's the one that sends both 0 and 1 to 0. And there are two morphisms that go from 0 to 1. That's the one that sends, there's one that sends 0 to 0, and the other one that sends 0 to 1. I'm calling them S and T here for reasons that'll be important later. So a simplicial set is just a, it's a functor from the opposite of this category to type. So that is to say, it's a pre-sheaf on the simplex category. So that is to say that it has a bunch of sets. So there's, if you take the functor x and you apply it to 0, you get a set. If you apply it to 1, you get another set. And so the first set we're going to call the objects. The second set is the morphisms. And using S and T, you can get the source and target of any given morphism. Using I on an object, you get the identity morphism. And so this thing kind of acts a lot like what you would want an infinity category to be. So this is a sort of putative definition. Now, there's some things that I believe are missing from this. You need more constraints on it, but this is sort of the raw meat of an infinity category. So the nerve of a category is, so nerve is a functor that operates on categories. So you give it a category, and it produces a simplicial set. So the n cells of that simplicial set are going to be the collection of functors from n to c. So now n here, the n in brackets, this is the set from 0 to n inclusive, but treated as a pre-order category. So that is to say, it's just got these n elements and the morphisms between them going in one direction. So this gives us a functor from categories to simplicial sets. And so our objective is to prove that this thing has a left adjoint and construct it. And that's going to take, given a simplicial set, it's going to give us a category, and that category is the homotopy category. So what does it do? So the idea is that you give it a simplicial set. It's supposed to produce a category. So that means we have a simplicial set. It's got these objects. It's got the morphisms. It's got the 2 cells. It's got the 3 cells. It just keeps going. And a category doesn't have that much information, so we've got to sort of throw away or collapse all the higher data. And so what we do is we take the objects to be the x of 0. We take the arrows to be x of 1. But whenever you have an x of 2, a 2 cell, that's going to identify the composition. So if you have this sort of composition triangle here, then sigma, which will be like an element of x2, is going to witness that this composition is supposed to be an equality. So it's a quotient operation. And so the main theorem here is that the nerve functor admits a left adjoint, which sends a simplicial set to its homotopy category. And we also need this fact that the nerve functor is full and faithful. So there's a sort of abstract reason for this adjunction to exist. So this is a special case of a result that's already in MATLAB. So if you have any functor, and so it goes from A to E, where A is small and E is co-complete, which is to say that it has all colimits, then the left conextension of this function, the left conextension of the functor is the left adjoint of this application of E. So this thing exists, and it gives us the left adjoint that we're looking for. So this is great, and we apply it, and then problem solved, right? Unfortunately, in order to apply that, like, you can almost apply this lemma, but we need that E is co-complete. And so that means that we need that cat has colimits. So how do you prove that cat has colimits? So we consulted the literature, and it seems that colimits are constructed as a corollary of the nerve adjunction, which is what we were trying to construct. So this doesn't really work. We actually need the nerve adjunction anyway. Okay, so fine, we'll try something else. So how do we actually construct this adjunction? And Emily had actually written a book on this, well, not just on this, but on lots of things, but this was one of them. You know, it's one-page proof. You can see the beginning to the end. That's the whole proof there. It's relatively simple, question mark. And so we tried to formalize this. It took us about 3 months. It took another about 6 months to get it actually put into MATLAB. And, well, so that's sort of what we're presenting here. It's definitely more than one page. Interesting. Okay, so I'm going to give you sort of overview of the proof, and then I'll go into sort of some of the complications that arose along the way while we were trying to do this. So the basic idea is that we're going to construct this adjunction as a composition of two adjunctions. So one of them, so here's a nerve that we want to construct the left adjunct ho. So ho is the homotopy functor. And then we're going to split it up into these two pieces. So we're going to introduce this middle bit. So this is simplicial sets. That is to say, these are functions from delta op to set. And so we're going to introduce delta less equal 2. That is the subcategory of the simplex category where we just take 0, 1, and 2. And so it has just two arrows in it, this is 0, 1, and 2, but of the simplex category, so it has all monotone functions between these sets 0, 1, and 2. And we can do the same thing, and we end up with two truncated simplicial sets. There's a sort of obvious function going this way, this TR2, that just takes a simplicial set and throws away all the higher data. So this is like we have a simplicial set, but it only goes up to 2. So if we have a full simplicial set, we can just throw away the higher data, and that gives us this function TR2. We have the nerve already, so we can compose nerve in TR2 and get nerve 2. That's this one over here. And this TR2 has a right adjoint, which is this cosc2. We get this by the same abstract nonsense as before. Using this lemma, well, the co-version of this lemma, we get a right adjoint, using the right con extension instead of the left one. And that gives us this cosc2. And so what we really need to do is, well, we have to prove this isomorphism here. And then we also have to prove that this ho2 exists. So those are the sort of 3 sub-goals that we need. We need to construct ho2. We need to prove the adjunction. And then we need to prove that the nerve is 2 co-skeletal, which is the same thing as saying that that natural transformation upsilon is an isomorphism. Okay, so I have to introduce another thing here. So a reflexive quiver, well, let's start with a quiver. So a quiver is like you take a category and then you throw away the identity and the composition. So you have a set of objects, you have a set of morphisms, and that's it. You don't have any laws or anything. It's just objects and morphisms. So there's a sort of obvious forgetful functor that takes a category and then just treats it as a quiver. And then that has a left adjoint. That's the sort of free category that's generated from a from quiver data. And so you can actually do the same thing with reflexive quivers, which sort of puts it in the middle here. So the top half, that was already in MATLAB, but this second part is what we had to introduce. So we defined reflexive quivers, which is just you have the reflexive, you have an arrow from a thing to itself. You don't actually have any laws because there's not really much you can say about that because you don't have the composition law. But you do have, so this is reflexive quivers, and then the category involves reflexive quivers and then reflexive prefunctors. So they're just mapping identities to identities. And so you can do basically the same thing. So you can construct, you have these forgetful functors going this way, and then you have sort of free constructions going the other way. And so this gives us, given a reflexive quiver, we can construct a free category. And so now we want to construct a we want to construct this Ho2. And the way that we do that is, okay, so we have, it was basically what I described before. So we have the set of objects, and then for our morphisms, we're going to take the x1, which have the certain beginning and end. And that defines our set hom m, hom AB. This is not a category because we don't have a composition operation. We just have these morphisms, but it is a reflexive quiver. So that's sort of what our input to the free category construction. So that gives us a free category using this data. The elements of that free category are essentially like strings of these x1 arrows. It's just sort of freely generated from these things. And then we take a quotient using this relation here. So like if we have an element of x2, this was the picture that I had before with the triangle. So we have an element of x2, and then this is going to give us a relation between the sort of formal composite that we get from this free construction and then the result. And okay, so we take the sort of hom quotient like this of the free category, and that's sort of the answer. That's the object part of the homotopy functor. And I'm not going to describe the morphism part, but it's the obvious thing, which, AKA it took us a month. So the tricky part of this so you also have to prove that this thing is an adjunction. And that means you have to construct a unit, a co-unit, and prove some triangle lemmas. So most of that is relatively simple. The tricky part of the construction of the adjunction is in the unit. And you can do so, you need this additional lemma. And so this is saying, okay, if we have a two-truncated simplicial set, and we're mapping into a category, so we have some f that maps the underlying reflexive prefunctors of x to c. Then under some condition, so I believe this is basically just saying that it sort of respects the quotient. If your f exists and respects the quotient, then it can lift to a map on the simplicial sets. So we have, these are for getting to reflexive quivers, and this is for getting the category down to a two-truncated simplicial set. So it's slightly less forgetting. And so when you actually have to construct this thing, okay, we have to construct a map, this f hat. This thing is operating on two truncated simplicial sets. This is a natural transformation. X is a functor. So this is a natural transformation of functors. So we basically have to define three different pieces. One of them for the 0, one of them for the 1, and one of them for the 2. Each of them is defined in completely different ways because one of them comes from the objects, one of them comes from the morphisms, one of them comes from these equalities. And so when you add it all up, you have to, defining the components, you have three things to do. Defining the naturalities, you have, for every monotone function between 0, 1, and 2, and all of the combinations, you have to prove some naturality lemma. There are 30. Okay. So that sort of leads naturally to what are the difficulties of this. One sort of interesting difficulty here is, uninteresting difficulty maybe. So the category of categories is a category. So you can use structures from category. So if you have a functor, it's both a functor and it's also a hom. It's a hom in the category of categories. Those have two different operators to give you. So if you want to describe a functor, you need to use, in MATLAB, you need to use this funny double arrow. If you want a hom in the category of categories, you need the single arrow. You can write them both between two categories, and they're both type checking and they're equal, and sometimes you get a goal that has half of them being, bold arrows and half of them not being bold arrows, and now none of the simp lemmas apply, and so you have to do some messy rewrites in order to try to find and fix all of those. Generally speaking, Mathlib prefers the sort of unbundled stuff for these categories. And there's also same thing for composition and identities. So it sort of makes a mess. There's also these sort of, well, I guess this is basically the same thing. So these highlighted areas are where you're rewriting with id, eq, id. This is talking about the id with one kind of font is equal to the id with a different kind of font. Okay. Also universe levels. I'm not going to read this, but this is basically saying that we're going to brush these universe details under the rug in a paper on category theory. Emily, her response to this is that, well, it's a bit embarrassing how poorly I understand the implications of various categorical constructions. And I am drawn to the dark side of type in type when I have to deal with these things. And so how do we deal with these universe errors? And my take on this is, I find it interesting how people, who don't have a lot of familiarity with Lean and are dealing with this stuff and have random universe errors come up, how do we deal with it? And one common piece of advice I would dispense in this situation, I would just say, just make everything type 0. Just don't worry about the universes. Like, I can clean it up later. It's fine. And so I think this is a sort of division of labor situation. So I felt competent to do the sort of universe stuff, but like when someone talks to me about reflexive prefunctors, I don't know what they're talking about. So I actually think it would be nice to have the dark side that Emily talks about. I think that we should have like a type and type flag so that we can just say, like, forget about the universes, let's do the sort of easy mode version of a thing, and then we can later go in and fix the universes. The basic issue here is that you have, I described there's the delta less than 2 and delta. I mean, ideally you would want to have one be a subset of the other, and Lean doesn't really do subsets. It does like inclusions, and then you have this secret inclusion that ends up in various places. We had to basically redefine all of, so this is stuff from the simplex category, but with 2's everywhere, to say we have all of the stuff over the 2 truncated simplex category, sort of just copying and pasting the lemmas, and then fixing how things are written so that Lean will be better about it. Also, this whole thing is about constructing colimits in cat. Cat is a 2 category. We're not doing 2 category theory. We're constructing strict colimits in cat. And so that means that we have to be doing some evil things. So we have to deal with equality of objects. We have to deal with equality of functors. And this adds another layer of mess. Yeah. So these are all totally invisible arguments on paper and not fun. There's a comment here that says, like, you don't want to do this, right? Like, Mathlib recommends against you having to use this stuff, and we didn't have a choice because we were trying to prove this thing that involved strict equalities. And for the infinity category theory, we really needed it to be strict equalities. The weak stuff was not good enough because it wouldn't generalize to the higher equalities. I'm going to skip this. So there's a related issue here with coherence, where you write down a long sort of whiskering sequence, and then there's something that needs to reassociate everything, and it's kind of a mess. Here, there's a tactic that was written by Yuma Mizuno on doing the bi-category reasoning, but it's not good enough to handle something here. I think it's the whisker exchange, which is why there's a sort of alternation of rewrite with whisker exchange and then call by category again. And so it would be nice to do both of those at the same time. Regarding the 31 naturality checks, the first time we did this, we split it into 9 cases. You can actually reason about it in groups. The Riehl, the version that was PR'd to mathlib allowed us to reduce it to just 4 cases, but mathematically there should just be 2. Basically, it has to do with the 2 generators of this collection of morphisms between 0, 1, and 2. So I think that collaboration between a domain expert and a formalization expert is very valuable. I don't think that we would be able to do this otherwise. There are still a lot of friction points, but I don't know. Maybe we can come up with some automation that will help with these things. And the Infinity Cosmos project is underway, so if anyone wants to get involved, there's some information on it. So that's all for me.